In theoretical framework where point-like particles in particle physics are replaced by one-dimensional objects called strings is known as string theory. This theory describes how strings instead of point-like particles propagate through space and interact with each other. Strings look just like ordinary particles with mass, charge, and other properties that are determined by the vibrational state of the string. One of the many vibrational states of the string corresponds to a quantum mechanical particle that carries gravitational force. Therefore, string theory is a quantum gravity theory. So within string theory, and I think many people have at least heard of what strength theory is, it's this idea that the elementary constituents of matter, little tiny particles, in the old way of thinking of things that are little tiny dots. The new idea of string theory is that within these little tiny particles there's something else, which is a little tiny filament that vibrates in different patterns. This little filament looks like a little piece of string, so the idea is that deep in the heart of matter, these little tiny vibrating strings. The theory attempts to address a number of broad and deep questions in fundamental physics. There are quite a few contributions of advances to mathematical physics from string theory that come to mind, including black hole physics, early universe cosmology, nuclear physics, condensed matter physics, etc. Physicists have been dreaming about a theory of everything for a long time, and because string theory provides a unified description of gravity and particle physics, it is a candidate for a theoretical model that describes all fundamental forces and forms of matter. String theory was first studied in the late 1960s as a theory of the strong nuclear force before being abandoned in favor of quantum chromodynamics. However, it was realized that the very properties that made string theory unsuitable as a theory of nuclear physics made it a promising candidate for a quantum theory of gravity. Bosonic string theory is the earliest version of what is today string theory, but it incorporated only the class of particles known as bosons. However, the theory later developed into superstring theory, where the connection between bosons and the class of particles known as fermions is called supersymmetry. Supersymmetry is a fantastically interesting mathematical symmetry that relates things that previously we thought were totally unrelated. You know what is the symmetry now? If I take this glass and I begin to turn this glass around, it's highly symmetric, which means that no matter how I turn it, it pretty much looks the same. Each point is related to every other point in a way that suggests that none is special. Each can be turned into the other point by simply rotating it. Similarly, there are class of particles in the world that are very important to us are the particles that make us up: electrons and quarks, the things that make up protons and neutrons. Those particles seem to be very different from a class of other particles by virtue of the fact that they actually spin around differently. Those particles that we all know about turn out to have something called spin a half. That's the way these little particles spin. But there are other particles that we know about that have spin 1. That's like the photon or the particles that communicate the nuclear forces, and there are some hypothetical particles not yet seen that would have spin 0. They wouldn't spin around at all. Supersymmetry is a mathematical symmetry that would relate all of those particles. It would say that in some sense each of those particles can be rotated into the others. Now, if that's the case, for that to be true, there will have to be a certain other class of particles not yet observed that the known particles we know about would turn into. Under this kind of symmetric rotation, those are the supersymmetric particles. So for the electron, its partner under this kind of symmetry is known as the supersymmetric electron, or this electron. If they're there, it will confirm this idea. If they're not, it either means that we don't have sufficiently powerful accelerators to create these particles, or it may mean that they don't exist. That's the current state. Some physicists have strongly criticized the approaches to physics using string theory and have questioned the value of continued research on string theory unification because the theory does not have a satisfactory definition in all circumstances and is thought to describe an enormous landscape of possible universes, which has complicated efforts to develop theories of particle physics. The golden age of physics witnessed two arising theoretical frameworks emerging from the laws of physics. The first is Albert Einstein's general theory of relativity, which explains the force of gravity and the structure of spacetime at the macro level. The other is quantum mechanics, which uses known probability principles to describe physical phenomena at the micro level. By the late 1970s, these two frameworks had proven to be sufficient to explain most of the observed features of our universe, from elementary particles to atoms to the evolution of stars and the cosmos as a whole. So the new idea of quantum mechanics in the early part of the 20th century was that, whereas Newton said, "Tell me how things are today, and I will predict how they will be tomorrow," universe is like a giant clockwork. I'll use my mathematics to turn the crank forward and predict how things will be, and the observations establish that that way of thinking about things was very accurate when applied to everyday objects like glasses, or to the moon's motion, or to a rock that you throw. Newton can tell you what will happen. You do the observation, and it does happen. Great. When people began to probe the microscopic realm, that whole structure began to fall apart, and in Some way you shouldn't be so surprised. Why should the laws that work on everyday scales also work on tiny scales? And it turns out that they don't. The laws of quantum physics, and the new idea of quantum physics is that you can only predict the likelihood, the probability of one outcome or another. But despite the huge success of modern physics, there are still many problems that remain unresolved. One of them is quantum gravity. A quantum theory of gravity is needed in order to reconcile general relativity with the principles of quantum mechanics, but difficulties arise when one attempts to apply the usual prescriptions of quantum theory to the force of gravity, and that's where string theory may come to the rescue. In the past several decades, physicists discovered certain mathematical transformations that identify one physical theory from another, called dualities. In string theory, there are a number of these dualities between different versions of string theory, and this has led that all consistent versions of string theory are subsumed in a single framework known as M-theory. Further studies have also yielded a number of results on the nature of black holes and the gravitational interaction. There are certain paradoxes that arise when one attempts to understand the quantum aspects of black holes, and work on a string theory has attempted to clarify these issues. What are the basic, fundamental, indivisible, uncuttable constituents making up everything in the world around us? So imagine we look at a familiar object, just a candle and a holder, and imagine that we want to figure out what it is made of. So we go on a journey deep inside the object and examine the constituents. So deep inside, we all know you go sufficiently far down, you have atoms. We also all know that atoms are not the end of the story. They have little electrons that swarm around a central nucleus with neutrons and protons. Even the neutrons and protons have smaller particles inside of them known as quarks. That is where conventional ideas stop. Here is the new idea of string theory. Deep inside any of these particles there is something else. The something else is this dancing filament of energy. It looks like a vibrating string. That's where the idea string theory comes from. They produce the different particles making up the world around us. This is what the ultra microscopic landscape of the universe looks like. It's built up of a huge number of these little tiny filaments of vibrating energy, vibrating in different frequencies. The different frequencies produce the different particles. The different particles are responsible for all the richness in the world around us. Since string theory incorporates all of the fundamental interactions, including gravity, many physicists hope that it will eventually be developed to the point where it fully describes our universe, making it a theory of everything. One of the goals of the current research in string theory is to find a solution to the theory that reproduces the observed spectrum of elementary particles with a single cosmological constant containing dark matter, and a plausible mechanism for cosmic inflation. While there has been progress towards these goals, it is not known to what extent string theory describes the real world or how much freedom the theory allows in the choice of details. In addition to the problem of developing consistent theory of quantum gravity, there are also many other fundamental problems in the physics of atomic nuclei, black holes, and the early universe, but we will cover them in another video. Thanks for watching. Did you like this video? Then show your support by liking, subscribing, and ringing the bell to never miss videos like this.